Okay, now let's talk about rotational inertia of a solid sphere about its center. So this is complicated, so try to follow along. Note that I've left the volume density from the last expression into here, and then the total volume is going to be exactly the same. So it will make our life a little bit easier. So how do we do this? So let's suppose that I have a solid sphere, right? So it looks like that. It is completely solid. Now how am I going to find dm's for my case? Well, the dm's in this case are going to be these small elements over here. If I take my origin to be here, then my radius r is going to be the capital R that goes, the little r is going to be this one, and also the capital R that goes here should be the same as that goes here and here and here and here and everywhere else, right? So in this case, if I was to consider this triangle here, this is my axes, right? If these are my axes, then this is going to be my radius r, right? This is the radius r, this is the radius r, this is the radius r, and so on and so forth. For a spherical coordinate, in this case, my angles will be d, theta, and phi. Now, how do I define r, theta, and phi for a spherical coordinate? So r is just plain radius that gets defined this way. Theta is this angle that falls down. And the limit of theta, so the limits for r are just 0 to r, right? The limits for theta are going to be from 0 to pi, right? So this is the angle, and because of symmetry arguments, we're only going to go from 0 to pi, right? We're not going to go 0 to 2 pi. And for phi, which is how fat your circle is, the limits are going to be from 0 to 2 pi. Okay, so these are the different limits for r, theta, and phi. Okay, so now for a sphere, we know that dv is going to be, so this dv is defined as x squared dx sine theta d theta d phi. Okay, this is what the definition for dv is in terms of its coordinates for a sphere that we know of. Okay, now in this case, in this particular case, what is x? For our particular case, x, which is actually dr, is this x over here, right? And that, if I was to look carefully, is actually equals to r sine theta, right? If this is r, this is going to be r sine theta, with this being the angle theta, right? If we were talking about y, it will be this line, and that will be r cosine theta. So I'm going to plug this value of x into here. What do I get? R squared sine squared theta dx sine theta d theta d phi, which is going to make it r squared sine cubed theta dx d theta d phi. Do you see how that one worked? Okay, so dv for a sphere is given by that value over here. Again, we know, what are we looking for? In this expression, we are looking for dm, right? So the moment of inertia for a sphere is going to be integration r4, right? r4 sine cubed theta. Oh, this should be an r now, right? So please make sure you correct that, right? This is going to be sine theta, sine cubed theta, dr d theta d phi, plus this rho, which I'm going to take out as m over v. Okay? So take a second to see what I've just done. So I've plugged the value of dm from here into here, and I've replaced this rho into here. That gives me my m over v, and dm will become rho dv, and the value of v for a sphere is given by that value. So it's r squared here and r squared here, so I've just joined them together. Now note this is a triple integration formula now, right? So it's going to have three integrations, 1 over r, 1 over theta, and 1 over phi. And we already know the limits of our integration. This is going to go from 0 to r. This is going to go from 0 to pi, and this is going to go from 0 to 2 pi. Okay? That means this is going to be m over v integration r4 dr from 0 to r sine cubed theta. The limits of integration is going to go from 0 to pi d theta, and from 0 to 2 pi d phi. Since they are not like r, theta, and phi are independent of each other, I can in fact split these up into these integrations. Okay? So the first integration and the last integrations are simple to see. They're easy to solve. But the middle one is going to be our problem child, right? So we have to do that separately. So let's try to do that on the board. Now just do it here and then plug the values back into here. So I'm just going to call this as I theta, okay? So let's try to solve I theta here. And then I'm going to erase it over here so that once we plug in the values, we won't need it. So this is going to be 0 to pi sine cubed theta d theta. In order to solve this integration, I can rewrite this as 0 to pi sine squared theta sine theta d theta, right? Sine theta becomes 0 to pi 1 minus cosine squared theta sine theta d theta. And since these are independent of each other, I can rewrite this as 0 to pi sine theta d theta minus 0 to pi cosine squared theta sine theta d theta. Well, this integration now becomes easier, but this one, we will need a u substitution for this one. So in this case, let u equals cosine theta. That means du is equals to sine theta d theta, right? And we have to change our limits of integrations as well. So when theta equals 0, u equals 1. And when theta equals pi, u equals minus 1, right? So this integration will change from 1 to minus 1 u squared du, which gives me u cubed over 3 from 1 to minus 1. This will be minus 1 over 3. Minus 1 over 3, right? This gives me minus 2 over 3, okay? Once that integration is solved, I can also do this integration, which will be sine, the integration of sine is minus cosine theta d theta. Is that true? Is it minus or is it plus? I believe it's minus. So this will be from 0 to pi. That means minus, no d theta anymore. So this will be cosine of pi is minus 1, minus cosine of 0 is 1. That will give me, for this integration over here, I can rewrite this as 2 minus 2/3, which can also be written as 4/3. So this integration answer is 4/3. So take a second and look through this integration. Make sure you know what I've just done. So I've just simply distributed these, solved for these, and come up with different answers, plug them back here, so that my final formula is of this form, right? Once this makes sense to you, the only answer we're looking for is 4/3. And I'm going to plug that back into here. So I will get, so I'm going to change markers again. Sorry about that, I dropped that. So this is going to be equals to m over v. This is going to be r5 over 5, correct? This I theta gives me 4/3. and this integration gives me 2 pi. Right? So these integrations were easy. This was the hard one, and we actually did the whole derivation for that. Okay? So if I'm just going to erase that one so that we don't get confused where one begins and one ends. Okay? Now, what is a volume of a sphere? The volume of a sphere is 4/3 pi r squared. Excellent. So this means I can rewrite this as m over 4/3 pi r cubed, right? Times 4/3 2 pi, right? So pi goes away, 4/3 goes away. I have an r5 over 5 that I just sort of just ignored. Can't do that. That gives me 2, and that goes away. So what do I get? I get this equals to be 2 by 5, right? 2 by 5 mr squared. So look it up. The moment of inertia of a solid sphere is equals to 2/5 mr squared.